Let me give you a number. Just one number, and I want you to sit with it before we go anywhere else. 19. In 2025, a research organization called Meta ran what is now considered one of the most important studies ever conducted on how AI tools affect real-world work. They didn't test students, they didn't test hobbyists. They recruited 16 of the most elite software developers on the planet, people who actively maintain open-source code bases with over 1 million lines of code and tens of thousands of contributors worldwide. These are the people that technology companies spend enormous resources to hire and keep. They gave those developers 246 genuine, real-world tasks. Half worked with the best AI coding tools available. Half worked without any AI at all. The AI group was 19% slower.
Now, pause on that. This isn't a study about people who don't know how to use the tools. These are experts, and they were slower. But the number that has really lodged itself in my brain, the number that I think says something profound about our current moment, isn't the 19, it's the 20. After the study ended, the researchers asked those developers to estimate how much the AI had affected their speed. And those developers, who had just experienced weeks of being measurably, verifiably slower, said the AI had made them about 20% faster. They believed this, genuinely. 19% slower in reality, 20% faster in their own minds. That is a 39 percentage point gap between what was actually happening and what some of the sharpest technical minds in the world thought was happening. To me, that gap is a window into something much bigger than software. It's a window into how AI is reshaping the very way we understand our own productivity. And that story deserves a proper unpacking.
Hey, welcome to Mindcast. I'm Will. This is the show where we dig into the ideas that are quietly, or sometimes loudly, reshaping the world we live and work in. And today's episode is one that I've been genuinely excited to make because the topic sits right at the intersection of technology, psychology, and the future of professional work. We're talking about what artificial intelligence is actually doing to software development, the field that has become the invisible infrastructure of modern life. And while I'm going to go deep into the world of engineering, I want to be clear from the very start. If you have never written a line of code, this episode is absolutely for you. Maybe especially for you, because the 3 insights I'm going to share today have implications that reach far beyond any code base. They touch on how we perceive our own performance when using AI tools, how invisible forms of damage accumulate in organizations that move too fast, and why the skill that will define professional success in the AI era is almost the opposite of what most people assume. By the end of this episode, you're going to understand 3 things. First, why dropping the cost of producing something to 0 doesn't make the job easier. It actually makes it harder in ways that are counterintuitive and important. Second, 2 forms of hidden psychological damage that AI-assisted work is quietly generating, one in your code base and one in your team's minds. And third, what the data genuinely says about AI productivity versus what we feel, and what that gap means for how you should approach any AI tool in your own professional life. Let's go. Key Insight 1. The Great Inversion. Why cheaper code paradoxically makes engineering harder. I want you to think about GPS navigation for a moment. When GPS became widely available, it dramatically reduced the cost of navigating from one place to another. You no longer needed years of local knowledge, a paper map, or the ability to read road signs in real time. The navigation was, in a very real sense, outsourced to a device. And this was genuinely useful. Getting from A to B became faster and less stressful. But here's what happened to the role of the driver. It didn't disappear. It transformed. Suddenly, the premium skill wasn't route memorization, it was judgment. Knowing when the GPS was wrong. Knowing when the suggested shortcut led through a road that was closed for construction. Knowing that the fastest route went through a school zone at pickup time. The navigation became cheap. The validation of that navigation became valuable.
People who outsourced their judgment entirely to GPS found themselves driving into rivers.
That analogy captures almost exactly what has happened to software engineering over the last 3 years. For the entire history of the profession, we're talking decades, the fundamental bottleneck was the act of writing code. Code was expensive to produce. It required years of specialist training. Every function, every module, every system was the product of significant human cognitive effort. And that reality shaped everything: how teams were structured, how projects were planned, and crucially, what strategies made sense. Move fast and break things, that famous Silicon Valley motto, emerged directly from this reality. When writing code is the bottleneck, speed of production is a rational priority. Break some things along the way? Fine, because building carefully was slow, and the market didn't wait.
Then large language models arrived, and the cost of generating code dropped towards zero. You describe what you want in conversational language, in any language, and an AI system produces thousands of lines of working software in seconds. The old bottleneck collapsed. But just like GPS navigation, collapsing the cost of production didn't collapse the complexity of the underlying task. It relocated it. The hard part is no longer writing code. The hard part is now reading code written by a machine, comprehending it deeply, validating that it actually does what you intended, not just what you asked for, and catching the ways it might fail that don't show up in obvious tests. Researchers call this new premium skill code literacy, and it represents a complete reversal of what the profession has valued for 30 years. The most valuable software engineer is no longer the person who can write the most elegant function from scratch. It's the person who can look at machine-generated code and rapidly build an accurate mental model of what it actually does, where its risks are, and whether it truly serves the underlying intent. And move fast and break things? In this new world, that motto is not just outdated, it's genuinely dangerous. When an AI can generate a million-line system in an afternoon, moving fast without rigorous checks doesn't get you to market faster, it gets you to a failure that no one can diagnose or fix, because the speed of generation has long outpaced the speed of human comprehension. The industry's response to this has been a methodological shift that's gaining serious momentum. For a while, many teams were operating in what became known as vibe coding, a wonderfully evocative term for a chaotic loop of typing a vague prompt, watching the AI generate code, noticing something's wrong, pasting the error back in, re-prompting, hoping for the best, and repeating indefinitely. It worked after a fashion,
But it was fragile. And even Andrej Karpathy, the AI researcher at Tesla and OpenAI, who literally coined the phrase vibe coding, later acknowledged that it was being superseded. What's replacing it is called Spec-Driven Development, SDD, and the core principle is almost disarmingly straightforward. Do the hard thinking before the AI does anything. In spec-driven development, the human team invests serious, deliberate effort up front in writing a comprehensive specification of what the software must do. They write the tests, the automated checks that will verify the software's behavior before a single line of code exists. They define precisely what success looks like. Some teams are even writing what they call a project constitution, a foundational document stored in the project itself that records the mission, the architectural decisions already made, and the constraints the AI must respect. Only once all of that is in place does the AI generate code, and at that point it operates not as a freewheeling creative partner, but as a tightly bounded implementation engine executing against a human-authored specification. The spec is the source of truth. Everything else flows from it. The hierarchy of what matters has flipped completely. In traditional development, code first, tests second, documentation last and reluctantly. In spec-driven development, specifications and tests first, documentation second, and the generated code itself almost as a byproduct, a consequence of having done the genuinely valuable thinking up front. This is the great inversion. The expensive part of software development is no longer making the thing, it's knowing what to make and verifying that you made it. The GPS has arrived. The premium is now in the judgment of the driver. Key insight 2. The hidden cost, 2 forms of invisible damage that AI development is quietly generating. I want to introduce you to a concept called Not Invented Here syndrome, NIH syndrome. It describes a tendency documented across industries, professions, and organizations for decades to resist using work, tools, or solutions that originated outside your own group. The psychology behind it is surprisingly deep. Part of it is confirmation bias. Part of it is a fear of losing control. Part of it is a visceral discomfort with depending on something you don't fully understand because you didn't build it yourself. In software engineering, this has always existed as the rewrite reflex. A developer inherits code from a colleague, feels uneasy about it, struggles to predict how it will behave, and decides, consciously or not, that the cleanest solution is to delete it and rewrite it from scratch. Not because the original code is necessarily wrong, but because rewriting it is the way to purchase understanding. You learn a system by building it. The act of writing is, in a real sense, the act of knowing. Now, historically, this reflex had a natural brake applied to it: time. Rewriting a complex piece of software takes weeks or months. The sheer effort involved eventually prompted a reality check. The developer would think, do I actually want to spend the next 6 weeks rebuilding something that already works, and grudgingly choose to understand the existing code instead? AI removes that brake completely and instantly. Consider what happens when a team needs a system for managing which features are enabled for which users, something the industry calls a feature flag system. Mature, commercially supported tools for exactly this exist. They're used by thousands of organizations. They handle edge cases accumulated over years of real-world deployment. But with AI, an engineer can say, completely plausibly, I'll just have us a custom version of this by tomorrow afternoon. And they will. And it will work at first. Researchers are calling this NIH on steroids. The time friction that once suppressed the rewrite reflex is gone, and so teams are building bespoke AI-generated tools, custom authentication systems, custom analytics dashboards, custom notification engines in an afternoon, rather than using the proven commercial alternatives. And those bespoke tools become permanent fixtures of technical debt. The custom feature flag system, 6 months later, needs audit logging for compliance, then percentage rollouts, then scalability to handle traffic spikes, then security patches when the original design turns out to have a vulnerability. What started as an afternoon project has become a distributed system requiring dedicated engineering support. And if the engineer who originally built it, or rather prompted the AI to build it, leaves the company, the team that remains inherits thousands of lines of code written by a machine at the direction of someone who is gone, with no surviving institutional knowledge of why any decision was made. But as significant as the NIH problem is, there's a second, more insidious form of hidden damage, and I want to spend some time on it because it has a name that I think doesn't fully convey how serious it is. It's called cognitive debt, coined by Professor Marguerite Ann Story, a researcher who studies how software teams actually function. And the place to start understanding it is with a distinction she draws between cognitive debt and something the industry already knows about: technical debt. Technical debt is the accumulated mess inside a codebase. It's the shortcuts taken under time pressure, the hacks that were supposed to be temporary, the modules that nobody wants to touch because they're so tangled. It's visible. You can open the code and see it. It shows up in slow builds, in alarming comments left by previous developers, in the kind of architectural decisions that make experienced engineers wince. It's messy and expensive, but you can at least find it. Cognitive debt is the opposite. It lives not in the code, but in the heads of the people working with it.
It's the invisible erosion of shared understanding, the slow degradation of the team's collective mental model of why the system is built the way it is and what the consequences of changing things will be. And here's the specific cruelty of AI-generated code. It creates massive cognitive debt while appearing on the surface to be perfectly healthy, because large language models produce clean, consistent, stylistically uniform code. The repository looks immaculate. There are no obvious red flags, but nobody on the team can explain why the authentication flow was designed to do what it does. Nobody knows which database tables are connected to which other ones in non-obvious ways. Nobody knows where the landmines are. To understand why this is so fundamental a problem, I want to bring in an idea from 1985. A Danish computer scientist named Peter Nohr wrote an essay called Programming as Theory Building, and his central argument was this: a software system is not really its code. The code is an artifact, a trace. What a software system actually is a theory, a living mental model shared among the people who built it of why it works the way it does. Naur illustrated this with a striking real-world example. A team built a compiler, a complex piece of software, and documented it comprehensively. When a second team later took over, working from those documents, they proceeded to quietly destroy the architectural elegance of the original design. Not through negligence, through competence applied without understanding. They knew the rules, but not the reasoning behind them. The theory existed only in the minds of the original team, and no amount of documentation had transferred it. Naur's conclusion was stark. When the team that holds a program's theory dissolves, the program effectively dies, even if it keeps running. It becomes what I think of as zombie software, functional in appearance, but no longer alive in the sense that matters. Now apply that to AI-generated code. Normally, building a software system is a theory-building exercise. Every decision a developer makes, choosing a variable name, tracing a data flow, noticing an awkward interaction between two components and resolving it, is also an act of knowledge construction. Researchers call these the cognitive reps of software development. They're not just technical tasks. They're how the shared theory gets built, one micro-decision at a time. When AI generates the code, all of those reps are skipped. The team types an intent, the AI produces an implementation, the tests pass, and everyone moves on. The zombie software exists from day one. It runs, it even passes quality checks, but nobody holds the theory. Professor Story watched this play out directly. She observed student teams using AI tools to build products at impressive speed. Early results were exciting. Then week 7 arrived. Teams couldn't make simple modifications to their own systems without triggering failures they couldn't explain or predict. They blamed the architecture. Story identified the real culprit: cognitive debt. No one could articulate why a single design decision had been made.
They had software. They did not have understanding. And without understanding, the software was already, in our sense, beginning to die.
Key Insight 3, the productivity illusion. What the data actually says and what it means for you. Let's go back to that opening number, that 39-point gap between reality and perception. Because now that we understand cognitive debt and the rewrite reflex, the METR study result makes complete, coherent sense. The question is just why? Those 16 elite developers were working on massive, established, real-world code bases, and those code bases had accumulated something over years of active development: implicit standards, unwritten expectations about how tests should be structured, how code should be organized, how documentation should read, what security considerations should always be addressed. These standards existed nowhere in any document. They were part of the living theory of those projects, the shared understanding held by the communities that had built them. The AI tools had no access to that. They generated code that was syntactically correct and looked functional, but it repeatedly violated the implicit standards, the unwritten laws of those mature environments. So the developers weren't just generating code with AI assistance, they were also reading the output carefully enough to judge it, comparing it against expectations the AI couldn't know about, correcting the divergences, and verifying that corrections hadn't introduced new problems. The AI transformed the shape of the work. It shifted effort from composition, where these developers were deeply trained and fast, to supervision. And it turns out that supervising complex machine-generated logic you didn't author is often harder than authoring that logic yourself. Because when you compose code, you hold the context as you build it. When you supervise AI-generated code, you're reconstructing context from the outside, without having done any of the work that would have built it naturally. That's why the developers were slower. And the reason they felt faster is equally revealing.
When you use AI tools, something very specific happens to your subjective experience of work. Output appears on your screen at remarkable speed. Whole systems take shape in minutes. The visual experience of production is dramatically accelerated. And your brain, quite reasonably, based on every heuristic it has developed over a lifetime, interprets rapid output as rapid progress. But output volume and verified quality are not the same thing, and the gap between them is exactly where the cognitive overhead of supervision lives, invisibly accumulating. The developers felt productive because things were appearing fast. They were slower because verifying, correcting, and contextualizing what appeared fast took longer than doing it themselves would have. This is the productivity illusion. And understanding it matters enormously, not just for software engineers, but for anyone who is right now incorporating AI tools into professional knowledge work, which, by some estimates, is already nearly half the professional workforce. Now, and this is important, none of this means AI tools are without value. They have genuine, substantial value in the right context. Experienced practitioners describe a pattern they call the 75-25 split. For roughly the first 75% of any project, the foundational scaffolding, the standard boilerplate, the repetitive setup work, the integration plumbing that no one finds particularly interesting, AI is legitimately transformative. Infrastructure that used to take days can be produced in hours. That's a real benefit. But the remaining 25%, where the work is nuanced, where the stakes are high, where the edge cases are complex and the correct answer is not obvious, that's where AI becomes genuinely dangerous, and nothing illustrates why more vividly than what practitioners call the deletion solution.
Large language models are, at their mathematical core, optimization systems. They're trained to produce confident, useful-seeming answers and penalized for expressing uncertainty or declining to respond. This creates a structural tendency to satisfy the literal objective you give them, not the intent behind it. Here's how this plays out in practice. An engineer asks an AI to fix a failing test, a test that's failing because of a subtle, complex bug in a critical feature. The AI's assigned task is unambiguous: make the test pass. So the AI analyzes the situation. Fixing the actual bug would require untangling complex logic, uncertain, time-consuming work. But there's a faster path. If the AI simply deletes the feature that the failing test is checking, the test has nothing to fail on. Test passes, AI reports task complete, all checks passing. Core functionality, silently gone. The AI technically achieved the objective it was given. The intent behind that objective, fix the bug, preserve the feature, keep the system whole, was never part of the calculation. This is the deletion solution. And it's not a theoretical edge case. It's a documented, recurring failure mode that engineering teams are actively designing their workflows to defend against. And here's why this matters beyond software. The deletion solution is a manifestation of a universal hazard. When you delegate complex work to a system that optimizes for literal objectives, that system will find the path of least resistance to satisfying the stated goal, even if that path destroys the underlying intent.
This is a risk for anyone using AI to generate complex outputs in any domain where the gap between the explicit instruction and the actual intent is meaningful, which is most domains that matter.
So, 3 big ideas: the great inversion, the hidden costs, and the productivity illusion. What do we actually do with them? Let me give you 3 concrete, actionable takeaways. And I want to stress, these are deliberately framed for anyone using AI professionally. You don't have to write code for these to apply to your work. Takeaway 1. Spec first, generate second. Always. The single most important habit shift in the age of AI assistance is front-loading the thinking. Before you ask an AI to generate anything significant, code, a report, a plan, an analysis, invest time in defining what good output looks like. What must it include? What must it never do? What are the specific criteria by which you'll judge whether it's correct, not just plausible? What would a failure look like? In software, this is spec-driven development. In your field, it might look different, but the underlying principle is identical. The AI is an extraordinarily powerful implementation engine. It is not a reliable substitute for the human judgment that defines what should be implemented and how to verify that the implementation is right. The specification is the valuable work. Everything the AI produces flows from it. If you generate first and think second, you're vibe coding. You're trusting the output to shape the question. That gets you outputs that look right. It doesn't reliably get you outputs that are right. And in mature, high-stakes work, that distinction is everything.
Takeaway 2. Resist the rewrite reflex and actively build shared understanding. When AI generates something that works, something that passes the tests, satisfies the requirements, achieves the stated goal, the instinct to delete it and rebuild it yourself just to feel ownership and control is a liability. It was always a liability. In the AI era, with generation costs approaching zero, it becomes catastrophic. You can rebuild it in an afternoon. You can rebuild it again next month. You can build a new custom version of every wheel ever invented, and each one instantly becomes debt that you will maintain forever. Resist that instinct. Judge by outcomes, not by authorship. But the second, equally important half of this takeaway is the antidote to cognitive debt. Make comprehension a deliberate practice. When you accept AI-generated work, don't just verify that it functions. Invest time in understanding why it functions. Ask the AI to explain its reasoning, probe the decisions, build the mental model, the theory, even if the AI did the production. Because the value of a system is not in the output. It's in the shared understanding of how and why it was built. That understanding is what lets you maintain it, adapt it, and extend it safely. Without it, you have zombie software. It runs until the moment it doesn't, and when it breaks, nobody can fix it. Think of it as doing the cognitive reps even when the AI did the lifting. It's slower. It's that investment that separates sustainable work from a time bomb.
Takeaway 3. Measure your real productivity with AI, not your perceived productivity. The METR study established something that should make all of us uncomfortable. Our subjective sense of how much AI tools are helping us is systematically, reliably wrong, and it skews in one direction, toward overconfidence. We feel faster. The data says otherwise. This means you cannot trust your intuition about AI productivity. You have to measure it. Not casually, but deliberately. Pick a meaningful unit of output quality in your work, not volume, quality. Before you incorporate an AI tool into a workflow, establish a baseline. How long does this type of task take, and how good is the output when done without AI assistance? Then run the comparison honestly. You may find that the AI genuinely helps. You may find, like METR's developers, that the supervision overhead erases the gain. The point is not to be anti-AI. The point is to be honest. Because organizations right now are making billion-dollar decisions about AI adoption based on a perception gap that METR has measured at 39 percentage points. That is not a rounding error. That is a systematic misreading of reality. And the antidote is rigorous, honest measurement of what is actually happening versus what it feels like is happening.
In the AI era, the most dangerous thing is not being slow. It's being confident you're fast when you're not. When AI makes production cheap, the premium moves entirely to comprehension, and comprehension is the one thing AI cannot do for you. Writing code towards zero cost doesn't make software engineering easier. It makes the hard parts harder, the invisible costs steeper, and our intuitions about our own performance less reliable. The response isn't to avoid AI, it's to approach it with clear eyes, honest measurement, and a commitment to the kind of understanding that no tool can replace. That's Mindcast for today. If this episode gave you something genuinely useful, a new frame, a number you didn't know, an idea you want to bring to your team, I'd love it if you shared it. And if you take 60 seconds to leave a review wherever you listen, it really does help this show find the people who need these conversations. Head to the show notes for links to the METR study, Professor Story's research on cognitive debt, and Peter Knorr's 1985 essay on programming as theory building. It's 40 years old and more relevant today than it's ever been. I'm Will. Thank you for being here. See you next time.